In this next module, I'm going to introduce you to Cox regression. So in this module, we're going to get to the multivariate regression technique called Cox regression. So Cox regression is sometimes also called proportional hazards regression, and that's because inherent in Cox regression is this assumption called the proportional hazards assumption that's very essential, and we'll talk about what that is. So you'll sometimes see it called that. It's a multivariate regression technique that you use when you have time to event outcomes, and it's the most commonly used regression technique for this type of outcome data. What do you get out of Cox regression? What you get out of Cox regression is simply adjusted hazard ratios. You actually don't get anything else. There's no intercept. You're not going to get an estimate of the underlying hazard function or the underlying survival function. You're just going to get the hazard ratios. But that's often okay, because often all we care about is what is the effect of age or treatment or smoking on the outcome, and we don't care so much about what the underlying function looks like. Just to compare with parametric regression, which we did last week, here are some results from an exponential regression that we ran on data that were comparing people with active hepatitis. Some received steroids and some were in the control group, and it was comparing time to death. When we fit an exponential model, we're assuming that the hazard rate is constant over time. So that model fit for the control group here, which is in red. The hazard rate was about 1.1% per month of time, 1.1% chance of death every month. So that was quite high compared with the steroid-treated group, which had a much lower hazard rate every month of about 0.5%. That corresponded to that we could actually draw out these nice smooth survival curves that you see on the right-hand side here. What Cox regression does is it says, well, what if I don't care exactly what the absolute value for the hazard rates is? And what if I don't care to actually draw out these smooth survival curves? What if what I care about from this study is just what's the difference between the treatment group and the control group? What's the relative difference in mortality rates? A lot of times that's all I'm after. And that's what Cox regression does. It says, let's not bother to estimate this hazard, this underlying hazard function. Let's just estimate the difference between these two lines, the relative difference in the hazard rates. The assumption here, of course, is that there is a single relative difference. Since the hazard rate can change over time, it could be the case that the hazard ratio could also change over time. If the hazard rate went up in one group but down in another over time, then there wouldn't be a single hazard ratio. But what we're going to try to do in Cox regression is say, well, if the relative difference between the two groups is constant over time, as it is if we're assuming an exponential here, then we can estimate the relative difference between those groups. We can estimate that hazard ratio, and we won't bother to estimate anything else. So in this case, you can see we were, again, the rate in the control group was somewhere around 1.1% versus about 0.5% in the treated group. So that would translate to a hazard ratio for treatment versus control of somewhere around 0.4 or 0.5. And maybe that's all we'll estimate. And in fact, when we ran a Cox regression on these data, I showed you briefly last week that if you run a Cox regression on these data, in fact, all you get out is a hazard ratio. The hazard ratio comparing treatment versus control was about 0.43, saying that the treated group had about a 57% decrease in their mortality rate. And this was statistically significant. Notice the output from our maximum likelihood estimation in SAS for Cox regression has no intercept. This is it, just the treatment versus control. That was the only predictor in the model. No intercept here. We're not bothering to estimate the intercept, but we can still get that hazard ratio, which is what we care about in this case. So what does the model actually look like? It's the same basic model as we use for parametric regression. We're modeling the log hazard. We're modeling the log hazard as a function of some baseline hazard, which may change over time, plus some increase or decrease in that baseline hazard function depending on your risk factors. The key to Cox regression, however, is we are not going to commit ourselves to any particular form for the underlying baseline hazard function. We're going to end up canceling it out in the likelihood and not bothering to estimate it. So that means that it would be perfectly fine if your log hazard for a particular group looks something like this. So maybe this is, some weird function. So maybe this is my reference group. This is the log hazard for my reference group. And then maybe my smoking group looks something like this. It's kind of similar, weird function over time, no easy mathematical function to describe that. But as long as the difference between my smoking group and my control group is roughly kind of the same at all different time points, then we can estimate the difference between those curves, the relative difference, and that is the hazard ratio. And we're just going to estimate that. And the hazard ratio will be represented by the betas in the model. Betas for all of our risk factors such as smoking and age and so on. So what we're going to get out of the model is we're going to cancel out those baseline hazard functions and only estimate the betas. And if you exponentiate the betas, you get hazard ratio. So let me show you that now. If you take the betas from the Cox regression model and you just directly exponentiate them, you will get the adjusted hazard ratio for that particular predictor, and that's just shown here. So imagine that we've got a Cox regression model that we fit, and we have smoking and age in the model. I've got, say, I want to do the hazard ratio for a smoker versus a non-smoker. So I'm going to take the hazard ratio estimate from the model for the smoker versus the non-smoker. But I'm not going to fill in anything particular for the baseline hazard function, which again is allowed to change over time. But I'm going to assume that they both have the same underlying kind of shape of that baseline hazard function. I'm going to assume it's the same for both, but that the smoker gets an additional increase in the hazard at all times because of the fact that they're smoking. I also have beta age. I have age in the model here. And I'm going to just hold age fixed because that's what it means to adjust in a regression model. So as long as we're holding age fixed, those are going to cancel. The underlying baseline hazard functions are going to cancel. And all we're going to be left with is that the smoker compared to the non-smoker, if we have a binary variable for smoking, if I exponentiate that beta for smoking, that will give me the hazard ratios for, say, the outcome here being lung cancer for smokers versus non-smokers, adjusted for everything else in the model. And notice that I never had to specify the baseline hazard function in order to get the hazard ratio. I can just cancel it out. So this would represent, if I take the beta for smoking and exponentiate it, I get the hazard ratio for smoking, in this case adjusted for age. Just to remind you that we can get hazard ratios for continuous predictors as well. So if I wanted to look at the hazard ratio for age adjusted for smoking, so from that same model, how would I get the hazard ratio for age? Well, I'm going to say, again, I want to compare somebody who's older to somebody who's younger. So this would be the hazard for somebody who's older divided by the hazard for somebody who's younger. If I assume that they have the same underlying baseline hazard function, I can cancel them out. I don't need to bother to estimate them. I'm going to fix smoking, say they're both non-smokers, or I could have said that they're both smokers, so that those will cancel out. So all I'm left with here is e raised to beta age, and let's say I want to compare somebody who's 10 years older to somebody who's 10 years younger, then it would just be beta age times 10. I would then exponentiate. That would give me the hazard ratio for a 10-unit jump in age. It works exactly the same as when we exponentiated betas from a logistic regression model, except now we're getting hazard ratios instead of odds ratios. Now the key assumption here is that we have proportional hazards. What I mean by proportional hazards is that the hazard ratio is constant over time, that those two hazard curves are parallel over time. Otherwise, that hazard ratio would be changing over time. There are many ways that we're going to learn to test the proportional hazards assumption. One of the simplest ways is to generate this log-log plot that we talked about last week. If the log-log plot is parallel, then that would tell you that the underlying hazard functions were also parallel, and therefore that the proportional hazards assumption was met. So we're looking for parallel lines here. This is the log-log plot for the steroid data. And so this will show you, well, it's not a perfectly parallel set of lines between the two groups. You can see that it's a little bit narrower, closer together at the beginning and a little bit further apart at the end. But as real data go, this isn't terrible. These lines look reasonably parallel as real data go. So probably proportional hazards assumption would be close enough here. That's one way to test that proportional hazards assumption. We're going to talk about a whole bunch of other ways.